Here I have a system of nonlinear equations. So how do we solve this? You've probably taken a linear algebra course, or at least learned how to solve systems of linear equations, but those methods don't apply here. Now in a previous video, I showed how to use what's either called the Newton's method, or the Newton-Raphson method, to solve a single nonlinear equation. So we might have something like this. X cubed minus e to the x power equals 14. And we saw that in order to solve this using the Newton-Raphson method, what we do is turn this into a root finding problem, because that's really what this is for. And we get there by subtracting 14 from both sides. X cubed minus e to the x power minus 14 equals 0. And now the solution of this would be the root of this equation, or a root of this equation. In that video, and if you haven't seen that, you probably should watch that to understand the rationale. But we found out that this method basically does this. To find the k plus 1th value of x, we use the current value of x, which is x of k, minus the function using x of k, divided by the first derivative of that function using x of k. That is, we find the first derivative of f, we plug in an initial guess, so we would have x sub 0 as our initial guess. We would plug that into f of xk here, so we use x0, plug it into the first derivative of that function, and this would give us our first estimate, x1. And then we repeat by using x1 over here to get x2, x2 over here to get x3, and so forth. We can do something similar here. First, we'll start off by turning this into a set of roots. So this then becomes x1 squared minus x2 squared plus 7 equals 0. And x1 squared plus x2 squared minus 25 equals 0. And so that then will give us essentially our f here. We'll have f of function x is equal to x1 squared minus x2 squared plus 7. This will be a vector. x1 squared plus x2 squared minus 25. And this is equal to our 0, 0 to begin with. So our vector here, x, is equal to x1 and x2. So we would start with an initial guess. So this would be the 0th version of this. So if I guessed, 5 and 14 were the correct values for this, I'd put 5 here and 14 here. Plug that into here to get what the function would look like for that. But we don't know, what do you do about this? How do we find the first derivative of this? Well, for this, we can use what's called the Jacobian. So it's a Jacobian matrix. And let's see how we would use that. So if we have m equations or functions and n unknowns, then the Jacobian with respect to some vector x uses partial derivatives. So we take the partial derivative of function f1 with respect to variable x and divide that, it's not divide that. It's a partial derivative with respect to variable x1. And over here we'll use that same function again. But we're taking the partial derivative with respect to variable x2 and dot, dot, dot. And eventually, since we had n unknowns, we're going to take the partial derivative with respect to x of n. And so everything on this line uses the first function. And then below that, we're going to take the partial derivative of the second function, f2, and take that with respect to variable x1. Partial derivative of f2 with respect to x2, dot, dot, dot. And we work our way down until we get to the mth function, partial derivative of f sub m with respect to x1. Work our way over, and so this will be the partial derivative of f sub m with respect to variable x sub n. So that's Jacobian matrix. For our example, m and n will be equal, but I'm simply pointing out to you that they don't have to be equal. Okay? So then if we think about what we had before, basically this right here. So for the one-dimensional case, we had x sub k plus 1 is equal to x sub k. These are individual variables, right? Because we're talking about the single equation version. This is one-dimensional 1D minus f of x sub k divided by the first derivative of f using x sub k. Well, now what we end up with is that the vector x sub k plus 1 is equal to the vector x sub k minus the inverse of the Jacobian. This is Jacobian. We would find the inverse of it, at least theoretically, times this right here. So why do this? Well, remember, it's not mathematically valid to have, well, especially in this case, f is going to be a vector. It's not mathematically valid to divide that by a matrix. And even if this was a matrix, these are not legal in matrix arithmetic. But we can multiply this vector by a column vector to get another column vector. Okay? I'm not going to do that though. There's a couple of potential issues here. One is that as these matrices get much larger, it's actually computationally more expensive to find the inverse of this than what I'm about to show you. And also, depending on the quality of this matrix, and the correct term really is the conditioning, but think of it as the quality. As the quality gets worse, this actually could lead to poorer quality solutions. So here's what we're going to do instead. So what do we have mathematically? Well, this is a column vector. This is a column vector minus a square matrix times a column vector. And this right here will be a column vector, which we'll call S. Okay? So what we have here is that if we think of S as being the inverse of the Jacobian times f of x. Okay, so it's a shape here. Column vector, and this is a square matrix. If I multiply both sides of this by the inverse of the Jacobian, or excuse me, the inverse of the Jacobian, which is just the Jacobian, and these had, well, I'll leave out the k for a moment. Then I get this right here. Because the inverse of this is just the Jacobian, and when I multiply that times this, I get an identity matrix, and we just drop that out here. So how does that help us? Well, now I can just solve the system of equations. So I have this square matrix, this column vector here is equal to a column vector, and just like when you solve other systems of equations, we normally write this as being ax equals b form. You're given a, you're given b, you solve for x. Well, that's what we're doing here. We're given this, we solve for s, and we'll do that each time. So that means what we will do then is that we will replace this right here, x of k plus 1 is equal to x of k minus the inverse of this with respect to x of k. What we will do is replace this by solving j of x of k, s of k, this is a vector, equals f of x of k. Solve this for s of k, which is just what this is, and then use x of k plus 1 is equal to x of k minus s. Okay, right, because this right here is s of k, so we're just subtracting that from this. But we'll do this as a two-step process instead of, this is really two-step anyway. You have to find the inverse of this and multiply by this. But this leads potentially to better quality solutions, okay? And computationally, it's faster anyway. Although for the size of the problem we're working, you'd never notice a difference. So what are we going to do here? So let's go back to the problem I showed you at the very beginning, which was this. So this is what f of x would look like, as I showed you before. And what's the Jacobian? Well, the first derivative of this with respect to, or first partial derivative, excuse me, with respect to x1 will just be 2 times x1 because this is treated like a constant, right? So we have a constant and a constant since there's no x1 term in either of these. So these drop out. That's this. Then we take the first equation, find the first partial derivative with respect to x2. We get minus 2x2. Repeat for the bottom row, and we get 2x1 and 2x2. So in each iteration, we're going to plug in the current guess for x to reduce these to vectors or a matrix here. So I've worked out the first couple iterations by hand to show you how this works. So I'm going to start off with our initial guess is 1, 1. And so that means I would plug 1 in here for x1, 1 in here for x2, so that'd be 1 squared minus 1 squared plus 7 is just 7. And then we have 1 squared plus 1 squared minus 25 is negative 23. Jacobian for this would be 2 times x1, which is just 2, minus 2 times x2, which is just minus 2. This would be positive 2, get that right there. Solve now for s sub naught, or s sub 0. By rearranging to do all this, we get negative 4 and negative 7.5 as our value there. Subtract that from 1, 1 and get 5, 8.5 as our initial guess. Because remember, once again, this is saying x1, the variable x1 is 5 and the variable x2 is 8.5 as an initial guess. Okay? I can tell you that when I created the problem, the true answer that I used to make this up was 3 and 4. So this is not a very good guess. So we would repeat. And now we use x sub 1 in there. So we would get this for the initial vector for that. This would be the corresponding Jacobian, the corresponding s value, s sub 1, and x sub 2 is equal to 3.4 and 5.19. So let's look at a Python program now that will carry out the rest of the steps, because this is really tedious to do by hand. So here I have my Python program. I'm going to use the NumPy library, which is used for mathematics, in particular things like matrices, vectors, solving a system of equations, things like that. Matplotlib is used for plotting, although I didn't actually do any plotting here. So I had just left that in from some previous program. Here's where I wrote a function that will allow me to pass in the current guess of x, and it returns an array that uses those values. Here's a function that will allow me to pass in the current value of x and give me the Jacobian matrix for those values, and it returns it. Here's where the program will get started. So my initial value of k, this is my iteration counter, is 0. I'm going to run this a total of 6 times. And here's our initial guess right here, 1, 1. Okay? So this really, in NumPy does not distinguish between column vectors and row vectors if it's just a one-dimensional vector. So even though I've written it like this, in NumPy terms, I could have done this and it would still work for what I've written here. Okay? So I'm going to get f of x using this value, the Jacobian using this value, then I'm going to solve for s. This is built into NumPy. This is their linear equation solver. Then I'm going to subtract s from x to get the next value of s, or x, excuse me. And then I print out those results. And you can see this is the entire program here. So let's look at the values I get here. So here's the values I initially had, 7 and negative 23. Here's my Jacobian. Here's my initial result for s, and here's my initial guess for x of 5 and 8.5. Then on the next iteration, I get this right here, which is what I also had on my piece of paper. So here, x is now 3.4 and 5.19, which, like I said, this is what I had on my piece of paper. Now for the second iteration, or excuse me, it's technically the third iteration. Here's f, here's j, or excuse me, the Jacobian. And what's our guess? 3.023, 4.14. Now in this iteration, we're down to 3 and 4, depending on your level of precision that you're looking for. If I said, what is the answer to 2 decimal places? This is 3.00, and this is 4.00, which is actually the correct answer. We'll keep going though. We'll see down, we're at this one actually, 3 and 4 point, a bunch of zeros, 6, 4. And then finally at this point it's saying it's 3.3 and 4, excuse me, at the level of precision we're looking at. We can tell it's getting better by looking at s. Because remember, s is the difference between the newest value of x and the current value of x. That is, we start with the value, at each iteration we have our current value of x and we're using it to produce the next value of x by subtracting out s. Well, look at s right here. This is 1.4 times 10 to the negative 9th and 6.4 times 10 to the negative 7th. So the difference between consecutive values of x's is really small. And that's what you would hope to get if this converges. Just like with the Newton-Raphson method for the one-dimensional case, your initial guess can influence not only how quickly you get to the answer, but whether or not you even get to the answer. If we chose different values, it'd be possible to come up with something that didn't work. In fact, I'll just try this real quickly just to see. I'm just making this up, so I don't know how well this is really going to work. So it may still work, it may not work, I don't know. So in this case, on 5 iterations, it still got to the correct answer. Although notice the difference between consecutive values here are not as good, so I would need more iterations here, but it looks like it's still getting to the correct answer. But once again, depending on the problem, initial guesses can heavily influence how well you get the answer. But that shows how to use the Newton-Raphson method at the two-dimensional case to solve a system of nonlinear equations.